In this tutorial, I'll demonstrate how to run a single zone simulation using Insight. To get started, you'll first need to choose between the single zone or the multi-zone applications. For this demonstration, we'll select the single zone option. From there, you can either create a new project or open an existing one. If you've already run a single zone simulation before, you can reopen the case using this icon. Additionally, you can open an existing single or multi-run simulation. Let's create a new project from scratch. The first input required is the wellbore geometry. We'll input an 8.5 inch wellbore diameter and a base pipe outer diameter of 6 inches. For the inner diameter of the base pipe, we'll use 4.92 inches. Next, we'll set the wellbore deviation, which is measured from the horizontal downward. For this example, we'll use 2 degrees downward inclination. We will use a zone length of 100 meters. This is the interval between the packers. And we'll set the simulation segments to 100. One simulation segment per meter provides sufficient resolution. Increasing the number of simulation segments will require more CPU time. Next, we'll specify the valves. There are many different types of valves to choose from. We'll limit the scope of this video to ICDs, and we'll go through the rest of the valves and their applications in later videos. Next, we'll specify the valve positions, which can be defined as a vector. This is a list of numbers separated by a comma, or by setting the min and max values and the number of valves. In this case, we'll place the first valve at 5 meters and the last valve at 95 meters. We'll use 8 ICDs along the 100 meter long zone. This results in a valve per 12 meters. We'll set the nozzle diameter to 4 millimeters. We will keep the discharge coefficient at its default value of 0.93. After that, we can choose the angular positions of the valves. 0 represents the valve facing out towards you. Alternatively, we can select the random location option. This will randomize the angular position of the valves. There's also an option to engage a coning model, which specifically analyzes what happens at the valve inlets. However, for the purpose of making the simulation go faster, we'll disengage all of these options. This means that the valve will produce everything that comes into the segment where it's located. Next, we will move on to the fluid properties. In the multi-zone Insight, we can also choose to calculate the fluid properties from black oil models. However, for this simulation, we will choose constant properties. These should correspond to your downhole properties. Next, we'll move on to the solver. We need to ensure that the single simulation is engaged. We'll set our initial time step to 2 seconds. And we need to choose a location for the project files. We recommend placing this somewhere on your local drive. Next, we will input the boundary conditions. We have the option to choose either a pressure or a flow rate boundary condition. If we choose a flow rate boundary condition, the program will calculate the pressure at the outlet required to achieve the specified flow rate. For this simulation, we'll use a pressure boundary condition. We'll set the reservoir pressure to 200 bar. We will also specify the productivity index for this zone. This is necessary since we're using a pressure boundary condition. In this section, we can also define the fractions of oil, water, and gas that enter the zone from the reservoir. If we provide a single value, it will be assumed that the fraction is equal along the length of the zone. We'll set the water and gas fractions to 0.3 with the sum adding up to 1. These values are constant throughout the entire simulation for a single run. We also need to provide the initial fractions present in the system when you start the simulation. We'll assume that the completion has the same amount of oil, water, and gas present when the simulation starts. Alternatively, we could set it up to be filled with 100% water and see how quickly it fills with either oil or gas. Then we need to provide the outlet pressure value. we will use 180 bar, resulting in a pressure drop of 20 bar through the whole system. If we run this simulation, we will get a dashboard where we can see what is happening in the annulus and base pipe with time. Here we can observe the graphs that display the state of the simulation. There's a sliding bar at the top that allows us to step through, pause, and replay the simulation. The annulus and the base pipe are displayed along with the saturations of oil in green, water in blue, and gas in red. As we have set the well to a 2-degree downward deviation from horizontal, we see that the gas accumulation at the high point of the zone, oil accumulation in the middle, and water accumulation in the lower right part. Below, we see various graphs displaying the phase volume fraction, flow rates, and pressure inside the annulus, valves, and base pipe. If we look at the air and the mass balances for the different phases, we can see that the plots go to 0. That means that the same amount of fluid enters the system from the reservoir as leaves the system through the base pipe. At this point in time, we know that the system has reached a steady state. We can left click and drag to zoom in closer. Double right click to zoom back out. As the system stabilizes, valve interaction and fluid segregation have reached a stable condition. We can see that the use of static ICDs allows for a higher flow rate through the gas valves due to the lower density. This could be opposite if we were simulating with autonomous valves that are designed to hold back gas. Thus, by simulating with different types of valves, you will get a better understanding of the different valve functionality and the effects of inflow performance. After completing the single zone simulation, if you're satisfied with the valve type and number of valves, you can use a multi-run in the solver to generate a pseudo valve based upon this setup. We'll demonstrate how to do this in a future video. In conclusion, this tutorial provides a step-by-step guide to single zone simulation using Insight with ICDs. The video covers the initial setup, including the wellbore geometry, zone length, valve position, fluid properties, and boundary conditions. It also provides an overview of the different options available for defining fractions of oil, water, and gas entering the zone. We hope that this tutorial is useful for those interested in modeling fluid flow in oil wells, and it provides a detailed look at the different options available in Insight. Thank you for watching.